Good morning, Year 12. So we're going to carry on with these two lessons of maths, and we're going to do some work on the student's t-test. Now, statistics is not a massive part of the A-level. There's only two statistical tests you need to know how to do, which are the student's t-tests and the chi-squared test. However, they're both incredibly important when it comes to doing any future biological work or any scientific work, to be honest. Knowing this kind of statistics enables you to do meaningful scientific research. And so we're going to learn it properly today, and I'll explain exactly what you need to know specifically for the A-level later on. But most of what we're going to go through today is extremely important for the A-level. Now, the t-test is a way of knowing whether there is a statistically significant difference between two pieces of data. So let's say I got 10 people from Britain and I got 10 people from Spain, and I measured their heights, and it turned out that the average height of the British people was 5'11", and the average height of the Spanish people is 6'1". Now, if you were in secondary school, then you could say immediately, well, that means that Spanish people are taller than British people. Because we know what an average is, we know how to calculate a mean. Of course, if you think about it logically, everyone understands that is not what that data is telling you. If you've only got a small number of Spanish people and a small number of British people, then there is no real way that that is going to tell you definitively that Spanish people have an average height that is higher than British people. Because you might just accidentally have pulled some tall Spanish people off the street or some short British people off the street. Now, the t-test will take the data you provide, will analyse it statistically, and will tell you whether there is a statistically significant difference between the data. So if I put in the heights of those 5 Spanish people and the heights of those 5 British people, it would churn out a number, and that number would tell me, well, probably there isn't really a significant difference between the heights. And the more people you tested, the more likely it is that the t-test will tell you, yes, there is a significant difference between the heights. So basically, it allows you to answer the question, is there a real difference between the two samples I've taken, or is it just down to chance? So let's go through this. If I click through. Right. Now, in order what you need there, broadly, you need the data to be normally distributed. Now, there's another test called the Mann-Whitney U test, which you will use when you get to degree level biology, as I'm sure you all will. And that's useful when the data is not normally distributed. But the vast majority of data is normally distributed. So pretty much every quantitative variable is normally distributed. And so most of the time you can use your student's t-test. The small sample size is not strictly necessary, and most of the samples you're going to be looking at are less than 25, because otherwise it would take far too long to do. And we're going to start off with this first term, the null hypothesis. Now, the null hypothesis is what you are trying to disprove if you want to find out something interesting. So the null hypothesis in this case says there is no difference between the two samples. And you will either disprove that null hypothesis, or you will fail to disprove that null hypothesis. So if at the end of this I can say I've disproved my null hypothesis, then there is a significant difference between the two means. Now, that word null hypothesis is only used because you can use a shortening for that, an abbreviation for that, and it's quicker than saying I have disproved the idea that there is no difference between the means in these samples. Instead, you can just say I have disproved the null hypothesis, and everyone understands what you mean. When you're talking about a student's t-test, if you say I've disproved the null hypothesis, you mean I've shown that there is a real difference between the two samples. There really is a difference in height between Spanish and British people. Fine. Now, here's the statistic, and it looks more complicated than it is. It looks far more complicated than it is, so please don't stress. So let's have a look at this. So T is going to give you a number, and I'll show you how to use that number later, but we're always trying to calculate T, and T we can then use to do our test. So x bar 1 is the mean of your first set. So let's say I was doing Spanish people's heights versus British people's heights. X bar 1 might be the mean of the Spanish people's heights. Minus X bar 2. Well, that would be the mean of the British people's heights. So you do one minus the other. One mean minus the other mean. And remember, always comparing two different samples. So you always get a mean for one, mean for the other. And you then do one minus the other. Divided by, and this is where it looks complicated but isn't, the square root of the standard deviation of the first set squared. That's also called the variance, but don't worry about that. If you do maths, you already know that. Over the number in the first set plus the standard deviation of the second group squared divided by the number in the second set. So as long as you know that X bar is the mean, S is the standard deviation, and N is the number in each group, there is no difficulty here. I strongly recommend you write down this equation and what each bit means, because we're going to use it a couple of times today, and you will absolutely need to know it. Right. So pause me there and do that, please. Okay, there's one more thing to add, and this is the third thing you need to calculate before you can do your test, and this is the degrees of freedom. Now, we will talk about degrees of freedom in just a second, but basically we're going to use them for our test. And the degrees of freedom in this case is just a fancy way of saying n1 plus n2 minus 2. So I've got 5 Spanish people and 5 English people. I do 5 add 5 minus 2 is 8. That's the degrees of freedom. So by the time you're ready to test the difference, you should know what your null hypothesis is. You should have null hypothesis colon what's your null hypothesis. There's no difference between Spanish and British heights. That's the null hypothesis. I should have my t. I should have worked that out. Can't do that in this case because I haven't given you any numbers. And I should have my degrees of freedom. Well, I know what that is. It's 8. That's what you need written down, and then you can do your test. And the way you do the test is using this thing. Now this is a t-table. Again, this is far more complicated looking than it really is. What we've got here is different levels of significance, basically different levels of certainty. And we are always looking to make it less than 5% likely that there is no difference, or that the difference is due to chance. So basically these numbers, we're going to use them in a second to work out whether there really is a difference. If we use this column here, these numbers here, then we can say, assuming that we get the correct number, and I'll show you how to do that in a second, that we are 95% certain that there really is a difference. The second thing you find is we always use 5% instead. We always use 5%. The second thing we find is the number of degrees of freedom. So here I have 8 degrees of freedom. And I scroll along to here and I find a number of 2.306. This is what we call the critical value. And in order for you to be able to say that I am 95% certain that there really is a difference between British and Spanish people, that it's not due to chance or the people I picked up, your number, your t number, which we calculated using this fancy equation, needs to be larger than 2.306. Larger. So if I do my t, I do all this sum, and the number I get is 2.4, then I can say, yes, 95% certain, more than 95% actually, because the number is higher than 2.306, and more than 95% certain that Spanish people really are taller than British people. It's not due to chance, definitely true. 95% true. If my number is smaller than 2.306, I have failed to disprove my null hypothesis, and I still cannot say with any level of certainty that Spanish people are taller than British people. Now, I could fix that by doing another test with more people in it, if I really am certain. But you're always looking for 5%, and your degrees of freedom is used to then kind of find your number, and you want to be bigger than your number. Now, if you want to be really certain, let's say I wanted to be 99.9% certain that Spanish people really are taller than British people. This is for some reason a big deal to me. Then I need to go further along. I need to go to 0.1%. It's the chance of this occurring by chance, I need to go down to 8 degrees of freedom and have a number of 5.041. Basically, that just makes it less likely, because now you need your number to be even bigger, and t tends to be quite a small number. Fine. I think this will be much easier for you if we have done this as an example. So, I'm going to give you an example. We've got limpet diameters, everyone's favourite. So, excuse me, they're measured on 2 sites to see if there's any difference due to location. So basically, I've got some limpets that face north, I've got some limpets that face south. I want to know if there's a difference due to location. First thing I'd like you to do is write down your null hypothesis. Try to do it without waiting for me to tell you it, or without looking. What is the null hypothesis here? So pause me if you need to and write that down. So the null hypothesis here is there is no difference in the diameter of shells in the different locations. Oh, and if you don't know limpets have shells, there's no difference in their diameters. Limpets are little mollusky things. Fine. So we've measured the diameters, so the null hypothesis, there is no difference. That's the null hypothesis. These are your numbers. Now, I'm going to ask you to use your t statistic, and I'm going to ask you to have a go at this. If you're doing it on a calculator, I recommend you doing it in small chunks. You're definitely doing it on a calculator. I recommend you doing it in small chunks. So I recommend you doing the standard deviation squared over n bit first for each one, and then adding it and square rooting it in little chunks. Now here I have given you s squared, so you don't need to do any squaring. You know, I'll let you get on with it. Pause me, have a go. Okay. So let's have a look at see if we've got it right. Again, I'm assuming that when I did the maths however many years ago, that I did this correctly. If somebody spots an issue, then my apologies. I don't think there should be one. So we've got 36.5 minus 46.2, all divided by the square root, and this should be square root of the whole thing, 50.5 over 28, add 53.7 over 27. And if you do that, you should get a number of 4.987, excuse me, 4.987. So 4.987 is our number. Now let's do degrees of freedom. How did we do that? We did n1 plus n2 minus 2. In this case, 55, is that? Yes, 55 minus 2, 53. Fine. So we've got a t of 4.987 and degrees of freedom of, yes, 53. I got it right off the top of my head. Good. And now let's use our table and have a look. Now this table goes on into infinity. You can have as many degrees of freedom as you like. So here's a bigger table. Right, that's as close as we're going to get onto this table. You could do it more specifically, but broadly, even up to 60 degrees of freedom, we get a number of 2 for 5%. Our number was 4.98, and so you can say, yes, 95% certain I can reject my null hypothesis, and there is a significant difference in the diameter at the 2 sites. Because your number, 4.98, is bigger by a long way than these numbers. In fact, you could scroll all the way along to up here, and you could say you're 99.9% certain. Because the 99.9% number is 3.46. And your number was 4.98. Right? Let's do one more, and I'm going to help you even less. This one's going to take you a while, I'm afraid, but this is the kind of the point of the lesson. It's a bit more topical. I wrote this one recently. Here's your idea. Now, a scientist calculated the number of coronavirus particles in a milliliter of some patient's blood after 5 days with the disease. So it's just a study of people who have just got COVID, or they've been given COVID deliberately as part of a trial, and they are going to test how many particles there are per milliliter of drug. And they gave 4 patients the experimental medicine, 4 not the experimental medicine, and there's your data. And here's what I'd like you to do with this data. So, 1, you want to calculate a mean for each. That should be very straightforward. So you can call that x bar 1 and x bar 2. Calculate the standard deviation for each is longer and more difficult. Did that last week. In all honesty, you just need to do it. Write a null hypothesis. Well, that's, again, fairly straightforward. Calculate t, if you're using your equation properly, shouldn't be too hard. What I'm going to ask you to do is to very carefully, what I'm saying is do not just type the whole sum into your calculator. It will go horribly wrong. So do it in small parts, like I said before, and then work out the degrees of freedom. So you should have 5 answers here. The first 2 will have a mean for each and a standard deviation for each. So in effect, you've got 7 answers if you like. So pause me. I anticipate this taking you a good, probably 10 or 15 minutes for some people. Different people are different levels of good at maths. It's a terrible way of saying that, but if you've got a graphing calculator, if you do maths, it'll be easier for you. If you do not, it'll be harder for you. The one thing I will say, you are unlikely to be asked to calculate t in a real test because it will take quite a long time, but you definitely could be asked to explain how to do it, or to interpret somebody else's calculation, or to explain the results of a t-test. So it's very helpful for you to have actually done this. So please do have a go at this. Pause me, take as long as you need at this, and just get yourself the numbers you need. So, let's have a go at this. So the mean with the drug, that's the first bit I don't expect anybody to have a difficulty with. The mean with the drug is 177.5. The mean without the drug is 718.5. So immediately, if you're a newspaper, you can immediately write the headline, "This drug massively reduces coronavirus particles." But is it actually true? Is it actually true? Is it definitely true? Or is this just randomly that these 4 people that they've picked happen to have some higher results? Fine. Calculate the standard deviation for each is the first step towards getting an answer for, is there really a difference, a significant difference? Standard deviation for with the drug I got as 207.94, and standard deviation, I should say without drug, I apologise, 567.13. Now, immediately you can look at this, excuse me, skip back too far. Immediately you can look at this and say, there isn't likely to be a significant difference here. Imagine you draw a graph of this data. Sometimes I get people to do it. You're probably lucky I'm not. If you drew a graph, a bar graph, with drug, without drug, imagine the height of the bars. 177.5 tall for with drug, 718.5 tall without drug. Immediately it looks pretty good. But then imagine adding the error bars. 177.5 add 207.94 is about 400. So you're going up to about 400 at the top end of this bar. 718 minus 567 is, well, it's going to be under 200, isn't it? Is it under 100? No. Under 200 anyhow. So the top end of the with drug bar is 400. The bottom end of the without drug bar is about 200. Those error bars are going to be overlapping massively. And that tells me immediately there's probably no significant difference here. And so if I was a scientist, I wouldn't bother wasting my time doing a t-test, because I could look at that and go, that standard deviation is ridiculously large for the without the drug. There's too much variation here. There might be one outlier. It might just be that this one guy has got loads of drug. So it's very unlikely that this is going to turn out to be the real answer. And certainly until I do some more samples, way more than 4, I'm not going to be able to say this is a significant difference. But you did the t-test anyway, because I told you to. So you should have got a number. I got 1.79. Now I'll be honest with you, I have left my calculator in school, so I'm using Excel for this, which isn't always reliable. I know the first 4 answers are reliable. T might be slightly off, but it seemed about right when Excel spat it out for me. So 1.79 is the number I got. Now, let's have a look at our table. I've already told you what the answer is going to be, but let's have a look to guarantee it for ourselves. We're at our 5% significant level. What was our degrees of freedom? Well, 4 add 4 minus 2 is 6. I hope you got 6. So we can go 5% here, and there it's 6. 2.447 is the critical value. That's the number I have to be higher than. My value I got was 1.79. So, unfortunately, I am nowhere near that significance value. I cannot be certain, and therefore the way you would write this, the probability that the results are due to chance, is greater than 5%, so we cannot reject the null hypothesis. There is no significant difference in diameter at the two sites, or at the very least, the two sites, I haven't changed it from earlier, in coronavirus particles in two areas. Fine. I can either write there's no significant difference, or if I'm fairly confident there would be if I got more samples, I can say it is not possible to show that there is a significant difference. It's probably the best way of writing that. Fine. So how would I fix this? Massively increase the sample size is the way to fix this. If you think about the sum we're doing, scroll back to here. If I increase these n's a lot, then suddenly these numbers get much smaller because we're dividing by larger numbers, and therefore the bottom half of this fraction gets much smaller, and so the whole number gets bigger. But if there's no significant difference, it won't make any difference. Fine. So, t-test. What I need you to get from today, and we're going to be doing a few of these over the course of the next few lessons, unfortunately. What I need you to get from today is what a t-test is, what it's used for, that it's used to test for whether there is a significant difference between two means, between two samples. I need you to get what a null hypothesis is. It's going to be important in the chi-squared test we do in year 13. I need you to understand how to calculate a t-test, though as I say, you're unlikely to have to do that in a real exam. If you go on to do any kind of biology, or any kind of science, to be honest, you will definitely need to know how to do a t-test. And that will include psychology, medical research, literally anything. And I need you to understand how to interpret that result, and that is the most important bit they definitely can ask you to do. Right? They can ask you to do this. Now, usually, what they will do is they will give you the critical values. They won't even give you the table. They'll say the critical value is 2.447. He got a t-value of 1.79. What does this mean? And you need to be able to say, well, the t-value is lower than the critical value, so there's no significant difference. So much as this scientist might like us to think that this drug worked really well, it doesn't. Or there's no proof that it does. Fine. If you can do all those things, you've understood the t-test, fantastic. We're going to do some more practice of this going forward. So don't worry if you haven't got it perfect the first time, as long as you're understanding the principles and you can see where you went wrong. I hope you have a very good afternoon, and I will look forward to seeing you back in school whenever we are able.